Hello everyone, today is the first edition of the Quantum Cosmos Seminar Series, and we're pleased to have Dr. Sotaro Sugishita from Nagoya University of Japan, who will be speaking about Rindler Bulk Reconstruction and Subregion duality in AdS CFT. So thanks Sotaro for accepting this invitation, and over to you.
Thank you for the introduction, and thank you for giving me this opportunity to talk about my recent work. This talk is based on this paper in collaboration with Seiji Terashima in Yuka Institute, Kyoto University in Japan. Okay, let's start. Okay, so constructing a theory describing quantum gravity is one of the long-standing challenges in theoretical physics. Strong string theory is a candidate. Nevertheless, we don't know the non-perturbative definition of string theory yet. However, we have a remarkable conjecture that quantum gravity emerges from a lower dimensional theory, that is holography, and this is the main topic of this talk. Okay, so the AdS safety correspondence is a realization of holography. So this correspondence states that d plus one dimensional quantum gravity or asymptotic anti-Dojita space-time is equivalent to.
Sorry, your slides are not moving. In case
Oh, sorry.
we can only see the first slide still.
Oh, really? Uh, can you see?
Yes, now we can see the second slide.
Is it?
Yeah, now it's moving.
Okay.
Okay.
And is it moving? Is it moving?
Now I can see only the introduction.
Oh, uh, uh, why doesn't work? I, I'm moving slides.
Oh no, it's not moving.
Oh, why?
Or maybe you can share the entire screen, then it will.
Enter screen. Okay. So let me stop sharing. Is it moving?
Yes. Yes.
Is it moving?
Yes.
Okay.
Yeah. Okay. Please continue.
And can you see pointer?
Yes, we can see the pointer.
Okay. Okay. So I'm explaining AdS safety correspondence. So d plus one dimensional quantum gravity on asymptotic AdS spacetime is equivalent to d-dimensional conformal field theory. And in the context of AdS safety correspondence, one proposal, which is called entanglement wedge reconstruction, was made. So this proposal says that bulk local operators in some bulk subregion can be reconstructed from CFT operators supported only on subregion of CFT. More precisely, we take a subregion in CFT, I call large A, and we can consider real Tachyonic surface associated with this subregion. Then this subregion, small a, is a region enclosed by this boundary and real Tachyonic surface. Then if this entanglement wedge reconstruction is true, we may have a subregion duality such that physics on this bulk subregion is the same as the physics on this boundary subregion. And one simple example of entanglement wedge reconstruction is the so-called AdS Rindler reconstruction. And I will explain what is this. And however, we show that the AdS Rindler reconstruction is incomplete. So our claim is that entanglement wedge reconstruction is invalid. Indeed, this claim was already made by my collaborator, Seiji. Okay, so this is the outline of my talk. I was asked to a pedagogical part for PhD students, so I will give a pedagogical review of AdS CFT correspondence. Then I will review bulk reconstruction. Then I explain the incompleteness of AdS Rindler reconstruction. And this incompleteness is related to the existence of some geodesics in AdS Rindler part, so I will explain that finally. Okay, so let's review the AdS CFT correspondence. So I first explain AdS space, anti-Dojita space. So D plus one dimensional anti-Dojita space is a curved space such that the Riemann curvature takes this form. So this is a very symmetric space, and this L determines the length scale. This LADS determines the length scale of this space. And this space is a solution of Einstein equation with negative cosmological constant fixed by this AdS length scale. And in this talk, I will set this AdS length scale to 1. And I will introduce the global coordinates in AdS spacetime. This is, we will often use these coordinates. And here tau is a time direction, and r is radial directions. And omega represents the spherical coordinate of d minus 1 dimensional sphere. So, and using these coordinates, a metric of this spacetime can be written by this equation. And the important point is that these coordinates cover the entire region of AdS space. And time slice, tau equal constant surface is given by, this time slice is given by this metric, this part of metric, and this represents d-dimensional hyperbolic space. So time slice of tau equal constant surface is hyperbolic space. And let's consider the boundary of this space. So asymptotic boundary is given by taking r goes to infinity. And metric on this large R surface is roughly given by this one. So we have tau direction and spherical direction. So the asymptotic boundary has a topology such that time direction times d minus 1 dimensional sphere. So it's a d-dimensional cylinder, like this. So AdS CFT correspondence says that d plus 1 dimensional quantum gravity on AdS spacetime is the same as the conformal field theory on this cylinder. However, I should note that not all CFTs are dual to usual gravitational theories. Here, usual means that a series becomes Einstein gravity at low energy. Only a special class of CFT can be dual to usual gravitation theories. For example, 4-dimensional n equal 4 super-Yaml theory. And such CFTs are called holographic CFT. And in this paper, they considered what the conditions. They consider the conditions that holographic CFTs have a gravitational dual. And one important property of holographic CFT is large n factorization. This factorization means that in a large n limit, the multiple point correlators can be given by a weak contraction rule like this. So it's a product of a 2-point function by ignoring 1 over n corrections. So this holds at leading order of 1 over n expansion. Here, I assume that operator O has a dimension which is much less than the scale n. So this large n factorization says that in the large n limit, low energy spectrum is determined only by 2-point functions. So it says that the low energy spectrum has a Hawk space structure, and this Hawk space-like spectrum is actually the same as that of bulk free fields. For example, if we consider a scalar primary operator with dimension delta, if holographic CFT has this operator, then in the bulk there is a scalar field with mass given by this relation. So mass is determined by the conformal dimension of CFT operator. And then we have a so-called BD-HM relation, which relates the asymptotic behavior of bulk scalar fields to the CFT operator. And this relation is used in the bulk reconstruction, which I will review later. And indeed, this relation can be derived from the explicit correspondence of low energy spectra between bulk and CFT. So at low energy, we have a correspondence such that D plus 1 dimensional free bulk quantum field theory on fixed spacetime is the same as the large n CFT on cylinder up to 1 over n corrections. Here I have some remarks. So I suppose n is large but finite. It means that Newton constant in the bulk is small but finite. So it means that Gn is non-zero, so Newton constant is non-zero, so we have to take into account bulk reactions for high energy states. But we don't consider such bulk reactions, so this low energy correspondence is valid only for low energy sectors such that we can ignore bulk reactions. So we should regard the free quantum field theory description as low energy effective field theory of quantum gravity below some UV cutoff, which may be Planck's energy scale. Okay, that is a review of AdS CFT correspondence. So I will review the bulk reconstruction. So we have the correspondence between the low energy sectors of bulk and CFT. So we can represent bulk local fields by CFT operators. This is called bulk reconstruction. And Hamilton covered Griffith's law, considered this bulk reconstruction, and they found this formula. So local scalar field at some point in bulk can be represented by some non-local operators in CFT. Here, this is integration of some CFT operator with a smearing function k, and this integration region is given by this blue region on the boundary. So let's review this HKLL reconstructions. So we consider we first quantize bulk free scalar field. So by solving this equation motion, the quantization can be easily done. So this is a mode function satisfying this equation motion. Here the Fn is some function of radial direction and angular direction. The precise form expression of this is not important here. And roughly this mode function becomes this expression in the large R region. Here, Yn omega represents spherical harmonics of d-1 dimensional sphere. Then, and also by normalizing this Fn appropriately, we can find that this coefficient n and n dagger are rather operators satisfying these canonical commutation relations. So we have quantized bulk free scalar. Then using this PDH relation, we can relate phi and CFT operator. Then CFT operator represented or expanded by bulk ladder operators n and n dagger. And actually this expansion with this commutation relation agrees with large n factorization rule in CFT. And here I said this positive frequency part, I call this positive frequency part O delta plus, and the negative frequency part O delta minus. Okay, so CFT operator is represented by bulk ladder operators. So let's reverse it and represent bulk fields by CFT operators. So we have obtained this relation with this one. So solving this inversely, we can represent this ladder operator by CFT operator, like this. And plugging this into the mode expansion of bulk scalar field, we can represent bulk scalar field by CFT operators. So this is a bulk reconstruction formula. So bulk local field phi is represented by CFT operators. And this integration region contains entire sphere. So this is called global reconstruction. And Sage simplify this, simplify or investigate much more this formula, and he found that only this right cone region is important in this integration. This is just a comment. Okay, so this is a review of global reconstruction. And the main point of this talk is we have this subregion reconstruction. So subregion reconstruction conjectures that some local operator in subregion can be reconstructed only using CFT operators in subregions. So we don't need entire sphere, operators on entire sphere. However, our claim is that this is no. We do not have this such a subregion reconstruction. So let's see that. Okay. Okay. So any questions?
No questions
Okay.
from me.
Okay. Thank you. Okay. So to show our claim, I will focus on three-dimensional AdS space just for simplicity, and discussion is similar in higher dimension. And in AdS3, we use two types of coordinates. And one is global coordinates that I reviewed. We have a time direction tau, and also, okay, so I changed radial direction r to rho. So I have a radial direction rho, and we have a angular direction theta. And the metric can be written like this. And this rho moves in from 0 to pi over 2. And then this global coordinates covers entire AdS3 spacetime. And another coordinates which are used is AdS Rindler coordinates, TR, Guji, Kai. They are related by global coordinates by these equations, but here these complicated equations are not important. Anyway, in these coordinates, the metric takes this form. And one remark is that this AdS Rindler coordinates cover only a part of the entire AdS space. And these coordinates cover this inside of this green region. And in these coordinates we have a killing horizon. So this time direction TR direction is killing vector, but this becomes null at Guji equals 0. So Guji equals 0 is a killing horizon for this time translation. This means that there is a horizon for observers moving with this time TR. This is an AdS analog of flat Rindler horizon. So in flat space, an observer moving or accelerating in this direction, there is a so-called Rindler horizon. Like this, we have AdS Rindler horizon, this blue surface. And introducing these coordinates u and v, future horizon is parameterized by v, b, and space direction chi at Guji equals 0. So this is future horizon. This upper triangle is future horizon. And the past horizon is parameterized by u and chi, and this is given by this past horizon is this lower triangle. So we have a horizon. Okay, next we consider boundary of AdS Rindler patch. So AdS boundary is given by Guji equals infinity. So in taking this limit, metric is given by this one. So it's conformal to Minkowski space with time direction TR and space direction chi, spatial direction chi. And actually, this boundary is a subregion of the cylinder because AdS Rindler patch is a subregion of global patch. And the relation between two coordinates at the boundary is given by this. And this AdS Rindler boundary is only a subregion of CFT, and so tau and theta coordinates is restricted in this diamond region. And in this diamond region, we can use this relation, and the metric is related or transformed like this equation. So cylinder metric is conformal to two-dimensional Minkowski metric, a flat metric with this conformal factor. So the tau equals 0 surface time slice is divided into two regions. One is TR equals 0 surface and others. So time slice is divided into two regions, A and its complement A bar. So roughly cylinder Hilbert space of CFT on cylinder is divided into two Hilbert spaces. And in region A, we have this relation, and we can use this TR chi coordinates. And this is conformal to two-dimensional Minkowski space. So using this time TR and by using the quantization with respect to this time TR, Hilbert space on this region A is the usual of flat chip. This Hilbert space is the same as that of CFT on two-dimensional flat space. And in this conformal mapping, CFT operator on cylinder is mapped to operator on flat space by this conformal up to this conformal factor. And this CFT flat operator acts on this Hilbert space. So this subregion of cylinders can be mapped to flat space. Okay, so using this fact, AdS Rindler reconstruction says that bulk local fields in AdS Rindler patch can be represented by the operators on the boundary of AdS Rindler patch, that is two-dimensional Minkowski space. So if AdS Rindler reconstruction holds, bulk local fields can be represented by this one using operator of CFT on flat space. However, we will see that some bulk modes cannot be represented as operators on holographic CFT on two-dimensional Minkowski space. Okay, to see that, let's quantize free scalar with respect to Rindler time TR. So this is the equation motion using AdS Rindler coordinates. Here, direction, we have translation symmetry for TR direction and chi direction. So positive frequency modes should have a plane wave modes, but the equation for Guji direction is complicated, so we have some complicated function, but we can solve this equation motion, and this complicated function in Guji direction is given by this. But I don't use this complicated expression, so we can ignore this. Anyway, this mode function of Guji direction behaves like Guji to minus delta at near the AdS boundary, or I choose such mode functions. So positive friction mode is given by these functions. So using these mode functions, we can quantize scalar phase. And the coefficient A omega lambda and A daga omega lambda satisfies canonical commutation relation. Okay, so I will say that omega is a coefficient or frequency of time, and lambda is frequency in chi directions. And important point is any omega and lambda in this integral are allowed. So there are modes with omega square is less than lambda squares. So okay, so we call such modes tachyonic modes, although they are not tachyonic in the bulk free theory. This is just a name. And so such tachyonic modes exist also in higher dimension, but Professor Kajuri told me that in AdS2 there are no such tachyonic modes. So yeah, but in this talk I will consider only higher dimensional AdS3 or higher dimensional AdS space. So I don't consider AdS2 space. And if so we have a quantitation of scalar phase, so we expect that naively the PDM-GM relation holds in AdS Rindler like this. So asymptotic behavior of bulk scalar phase agrees with CFT operator. And actually this naive relation was assumed in literatures on AdS Rindler reconstruction. So if we believe this relation and using this mode expansions, this operator O is represented by ladder operator A and A dagger. And solving it inversely, we may express this annihilation operator by this operator O, or we can also represent bulk local fees by this operator O. However, if this operator O is a CFT operator, it implies that the generalized free spectrum of CFT on flat spacetime contains tachyonic states created by these mode operators with tachyonic modes. However, the holographic CFT should not contain such tachyonic states. It contradicts with the standard two-point functions on the vacuum. So this cannot be CFT operator. And I have some note. These tachyonic modes are called evanescent modes in the paper by Ray and Rosenhaus. And they also discuss the difficulty of reconstructing these modes, although they consider that these modes are in CFT. So the last claim is different from our claim. So the holographic CFT should not contain tachyonic states. And indeed, we know the low energy spectrum of large and holographic CFT on flat spacetime. This can be obtained from the bulk reconstruction on the Poincare patch. And using this Poincare patch reconstruction, a large N CFT operator should have this mode expansion. And the important point is that this operator does not contain tachyonic region, tachyonic modes, and this operator with the tachyonic modes reproduce the standard two-point functions on the vacuum. So the operator obtained by naive extrapolation relation is not a safety operator on flat space. So therefore the AdS Rindler reconstruction does not hold.
Sorry, are you saying that it does not hold because it does not give the standard two-point function?
Yeah.
Oh, okay. Okay, please continue.
Yeah. Or if this is CFT operator, then the spectrum of holographic CFT has a tachyonic state, so it's problematic. Okay. So from CFT point of view, tachyonic modes are problematic, but the tachyonic modes itself are not problematic as a bulk-free theory without UV cutoff, because we have seen that scalar fields have, using standard quantization, we have seen that tachyonic modes exist in free scalar fields. And including these tachyonic modes, the standard completeness relation holds. This relation means that an operator at some point in the global coordinates should be the same as operator in Rindler quantization if these points are the same. Here I naively assume that global Hilbert space is a tensor factorized. So using these completeness relations, we can consider the Bogoliubov transformation between global modes and AdS Rindler modes. But this is true only if we don't have a UV cutoff. As I said in the introduction, we consider effective field theory below a UV cutoff or Planck scale. So we are considering EFT of quantum gravity. Then this naive relation it's not clear that we have these relations in quantum gravity. Indeed, we can show that if we use these naive Bogoliubov transformations, we can show that the low energy modes with respect to AdS Rindler time contain high energy modes in global time. In particular, the tachyonic modes in AdS Rindler quantization have dominant contributions from high energy modes in global quantizations. This statement implies that tachyonic modes do not exist in low energy effective field theory, or they are trans-Planckian modes. And this discussion that low energy modes in Rindler patch contains high energy modes in global patch sounds similar to the so-called trans-Planckian problem investigated by or pointed out by 't Hooft. And maybe this property is a generic property of horizons. And I think this is the fundamental problem in quantum gravity, and I'd like to investigate this problem much more. Okay, so I have explained the incompleteness of AdS Rindler reconstruction. And this incompleteness comes from the existence of tachyonic modes. And I'll explain that these tachyonic modes are related to some null geodesics. Okay, so I will
Sorry,
explain.
just if you can go back. So, what was the problem? You're saying that tachyonic modes are high energy modes.
Yeah, so
In,
if we consider effective field theory, low energy effective theory,
uh,
maybe these tachyonic modes do not exist in such low energy circuit.
yeah, so if you give a UV cutoff, you are saying that these modes won't exist. But if
Yeah,
you allow all energies, then these modes are also there, right? You're saying if I make a UV cutoff, then I won't get the knife, what you are calling knife Bogoliubov transformation. Is that
yeah,
correct?
yeah. We cannot trust this naive Bogoliubov transformation.
If there is a UV cutoff.
Yeah, if there's
Okay, okay, thank you.
and as I said in the introduction, we are consider only this free QFT description is valid only for low energy sectors. So there are, and if we consider this region, there are there must be UV cut or Planck cutoff, Planck energy cutoff. Okay, so I'll talk about geodesics, a relation between tachyonic modes and geodesics. I will explain that in AdS Rindler patch, there are null geodesics never reaching the asymptotic boundary of AdS Rindler patch. And, and these null geodesics come from the past horizon and goes to the future one without reaching the asymptotic boundary. And the existence of these geodesics are related to the existence of tachyonic modes. I will explain this one. And in this paper, they also argue that such null geodesics are related to a difficulty of subregion reconstruction. Okay, so let's consider null geodesics. Here, S is the affine parameter of this geodesics. And TR direction and chi direction are we have translation symmetry, so we have conserved quantities associated with these two vectors. And two conserved quantities are I call omega tilde and lambda tilde. And I'll set the ratio of these ones as B. And if you simplify geodesic equation, you can find that geodesics is determined by this equation. Here, this B appears in here. And behaviors or solution of this equation depends on whether B is greater than 1, the absolute value of B is greater than 1 or not. So let's first consider the case that B is greater than 1, or B squared is greater than 1. Then in this equation, this quotient is negative, but the left-hand side should be positive. So Guji has to be the region that this this one, the equation inside the bracket is positive. So Guji has the upper bound fixed by the value of B. So this says that Guji never reaches the boundary. Boundary is given by Guji equal infinity. So Guji cannot be infinity. In fact, it's easy to solve this equation. And the solution is given by this one. So if by looking at this one, you can find that If tr equals to minus infinity, g to 0, so it starts from past horizon, and tr goes, if tr increases and tr reaches infinity, g goes goes to 0 again, so it goes to the future horizon. So this geodesics comes from past horizon and goes to the future horizon. Next, let's consider the solutions for geodesics with p is less than 1. The solution is given by this one. So from this equation, says that it starts from the boundary g equal infinity at some time tr equal t naught. T naught is arbitrary integration constant of geodesic equation. So it starts from here and approach it to the future horizon, g to 0 if tr becomes infinity. Or it starts from past horizon and reaches boundary like this. So this is boundary. So this is boundary horizon geodesy. And I will explain the relation between these geodesics and mode expansion in linear patch. So let's see what modes dominantly contribute to the wave packets were localized on the geodesics. Here, for simplicity, I focus on high frequency modes, such that we can ignore the mass and AdS curvature. But of course, omega lambda should be much less than the Planck cutoff. And if we can ignore these terms, such high frequency modes propagate almost like, and we can use a geometrical optics approximation. And we focus on a point on the geodesics. And around near this point, we can use locally flat coordinates. It's given by this one, t bar, g bar, chi bar. So they are locally flat coordinates. So the dominant modes of wave packet localized on this geodesics is given by plane wave with velocity fixed by this geodesics. So this plane wave has this component. Here, this v bar chi is the velocity of chi direction in locally flat coordinates. So if we go back to the original coordinate chi and t, this v bar chi is given by this one, and you can find that this component becomes this one in the original Rindler coordinates. On the other hand, we have seen that positive frequency modes in AdS linear patch is given by this one, so this mode has this component. And comparing these ones, you can find that this B is the same as lambda over omega. So the geodesics with parameter B consists of modes which have the mode frequency satisfy this equation. So if B is greater than 1, that is horizon geodesic. This means that omega square is less than lambda square. So this corresponds to tachyonic modes. On the other hand, if B is less than 1, they correspond to non-tachyonic modes. Okay, so the existence of horizon-to-horizon geodesics is related to tachyonic modes. Okay, so tachyonic modes cannot be reconstructed by CFT on subregion A. So we can reconstruct only a part of a bulk quiz, such that to ignoring or throwing away tachyonic modes. So this, however, by if we uh, if we ignore these tachyonic modes, they are not low. These bulk quiz are not local operators. And this non-local operator can be reconstructed by CFT on subregion, like this. If we include tachyonic modes, this smearing function is ill-defined, as pointed by HKLL paper. So if we have in tachyonic modes, we have to perform an analytic continuation, or we have to regard this smearing function as a distribution. But if we throw away tachyonic modes, this smearing function K is well defined. And also, I say that subregion duality does not hold, but a weak version of subregion duality holds. That is, CFT operators on A can be represented by bulk operators on this subregion small a. So schematically, the Hilbert space of subregion, CFT subregion is included in bulk Hilbert space, but the inverse does not hold, as I said. Tachyonic modes cannot be reconstructed by CFT. Okay, so our results say that CFT on subregion A can reconstruct the well-localized wave packets only if they reach subregion. DEM is the domain of dependence of subregion A. So we cannot reconstruct horizon-to-horizon geodesics because they never reaches this DA. This is consistent with Terashima's bulk reconstruction. He studied how well-localized bulk wave packets are described by CFT and obtained the same conclusion. Okay, let me summarize my talk. So we show that the AdS Rindler reconstruction is incomplete. Tachyonic modes in AdS Rindler are the origin of the difficulty. And these tachyonic modes are related to horizon geodesics. So our claim is that entanglement wedge reconstruction does not hold, although a weak version is okay. So there are many discussions based on entanglement wedge reconstruction, so it's interesting to reconsider these discussions if we do not have entanglement wedge reconstruction. Okay, that's it. Thank you.
Thank you. So I will stop recording and then we will open the floor to questions.